Welcome to Intro2Astro 2024.
Hi, and welcome to another module of Intro2Astro. I am Maria Vincent from the Institute for Astronomy in Hawaii. Let's dive into a little bit of instrumentation and look at a technique that has revolutionized imaging in astronomy. The title slide features a photograph of the two Keck telescopes at the summit of Mauna Kea, a large dormant shield volcano on Big Island, Hawaii. There are a few aspects of the slide that may seem foreign to you, which I'll talk about during the course of this presentation. What's AO? What are the two yellow beams coming out of the telescope domes? And why do we have telescopes on a volcano? So to start, let's ponder on a simple question that motivates the technique described in the rest of the talk. Why do stars twinkle? This little animation explains that. Starlight goes through several layers of atmosphere and it undergoes refraction at each layer. In addition to that, its propagation is affected by the winds in the atmosphere and by areas with different temperatures and densities. This is broadly referred to as turbulence. So a combination Our atmosphere is not exactly homogeneous. You can imagine air as being broken into different parcels or cells. These cells have different temperatures and densities, and they interact with each other. As a result, the image of our target seems to be blurred or smeared or even scintillating. This is called atmospheric seeing and is quantified as the size of the target as imaged by the telescope before any correction is applied. This cartoon is here just to reiterate the complicated physics of turbulence in a very simple fashion. The incoming light is originally a set of plane waves, which then pass through patches of air represented by the red clumps. And out comes a distorted wavefront. And this happens over several layers of atmosphere over a long distance before reaching the ground. To put this in more optical terms, each of the air packets or cells act like little lenses, and the starlight has to propagate through multiple lenses before reaching the telescope. Ideally, if the light rays are parallel, the telescope's optical system can focus those rays to a point. But in this case, they're not parallel. The distorted wavefront thus creates a problem now because the light rays cannot be focused to a point and we thus cannot get a sharp image. Way of dealing with turbulence is to observe from a higher elevation. That's one reason why astronomers choose to have telescopes on summits of mountain, or in this picture, a dormant volcano in Hawaii, which on a map looks like a spot in the middle of nowhere. Mauna Kea is an excellent location for several other reasons as well, but just the elevation of 4,205 meters, which is almost 14,000 feet, gives an advantage to overcome some amount of turbulence, as most of the issue with the mixing of air parcels occurs at lower altitudes. To combat turbulence more technically, we have a very elegant technique called adaptive optics, or AO for short. With AO, we can get sharper images of fainter objects and study them in greater detail. On a grand scale, the AO workflow is quite simple. The objective is to correct the distortions in the incoming wavefront or the incoming waves of light. Incoming wavefront hits and bounces off a deformable mirror, which is a mirror that can change its shape. The wavefront is split into two parts by the beam splitter right here. One part of the wave goes to the detector, the other part to the wavefront sensor. A wavefront sensor measures the distortions in the wavefront, and accordingly, the mirror can deform or change its shape to correct for these distortions. In the end, the corrected wavefront enters the detector, which gives a sharper image, as you see on the little computer screen. Right there. Now let's take a look at some before and after correction images to get a better sense of how helpful adaptive optics is. Look at this blob. It's big and fuzzy at the start, and it would have seemed like a single large star. But thanks to AO, we can achieve a higher angular resolution than what's determined by seeing. In fact, it's going to be close to the actual resolution of the telescope itself. And we see that it's not one star, but it's actually a binary right here, and there's a third star off to the top right. This is a classic animation to demonstrate how useful AO is. Turning on AO, we can actually see the individual stars around the galactic centers. This is especially important as the presence of a supermassive black hole at the center of the Milky Way was determined through years of observing and charting the orbits of nearby stars. Without AO, that's just two bright spots on a pear-shaped blob, but the enhanced details after using adaptive optics reveal a better image of Neptune. This is a simple schematic representing the main components of an adaptive optics system. Let's take a closer look at the two of the main parts. The deformable mirror is what determines the shape of the wavefront sent to the science detector and wavefront sensor. It comes in different types. Each type has its own kind of mechanism that allows for the mirror's shape to be changed based on what the incoming wavefront looks like. So in this animation, you can see the difference between the distorted and corrected wavefront on the left and the right respectively, and how that shows up on the detector. Once AO correction is applied by changing the shape of the mirror, as we see in a center, the light from around the central source is concentrated in the core of what we call a point spread function, which looks like a Gaussian. The intensity increases in the core, which is the central part of the curve, and decreases in the halo, the outer part of the curve. Thus, we get a sharp point-like image as seen on the right. These are just a few types of deformable mirrors. The segmented mirrors are made of separate segments with small gaps and are controlled by actuators, which are little piston-like devices whose motion helps control the shape of the mirror. Bimorph DMs have piezoelectric wafers bonded together with an array of electrodes between them. The front surface acts as a mirror. What you see in this image is the wiring on the back. A continuous phase sheet DM has actuators that modify the shape of the DM, but instead of being broken into segments, is just a single thin glass sheet, and hence the name continuous phase sheet. Microelectromechanical systems, or MEMs for short, are a new innovation that's quite unconventional and also very small as a penny, in fact. They are fabricated using microfabrication methods used for integrated circuit chips. Their small size and potential for mass manufacturing make them potentially inexpensive. Now let's go to wavefront sensors. Just as the name suggests, it senses the wavefront, that is, measuring the aberration or how much deviated the incoming wavefront is from being perfect. Different wavefront sensors have their own working principles to measure this aberration. Two common types, at least the ones I have come across for my work, are the Shack-Hartman and the pyramid wavefront sensor. And the Shack-Hartman sensor, which you see on the right, we have a collection of small lenses called a lenslet array. Each lenslet takes a part of the light coming from the pupil where all the light enters and forms the corresponding image on the same detector. On the top, you see the case of a perfect wavefront where all the images formed by the lenslets come together in a neat grid pattern on the detector. As soon as the wavefront is distorted, as you see in the bottom image, you see that the images are formed far away from the nominal positions. Sometimes close, but in the outer cases, you can see it's quite far. The deviation in the X and Y direction corresponds to the wavefront slopes, which is communicated to the DM, and it assumes the needed shape. A pyramid wavefront sensor, as the name suggests, involves a pyramid, and that's what you see below here. The light enters from the top vertex of a transparent pyramid, which splits the wavefront into 4 beams, each producing an image of the pupil. For a distorted wavefront, the intensity distribution among the pupils will change. The local wavefront gradients can be obtained by recording the distribution of intensity in the pupil images. The wavefront aberrations can be evaluated from the estimated wavefront gradients. To apply the wavefront correction we've talked about so far, the wavefront gradient or the distorted wavefront needs to be measured somehow. There should be some sort of a benchmark to measure the turbulence. So, what is that? We call that a guide star. As written here, it is essentially a reference point to measure the distortions in the incoming wavefront and apply the appropriate shape to the DM. It comes in two types, and you've actually already seen one type. Remember the laser beams from the title slide? That's for a guide star. We can thus create an artificial guide star using a laser beacon to illuminate a spot in the atmosphere. Or we can use a bright star close to a target if such a star is present. If you recollect the AO system schematic, it's a lot of parts. All of that has to fit somewhere in the larger telescope hardware, right? Typically, it is fitted behind the main telescope mirror. The exact position depends on the other parts and the mount setup of the telescope. The image on the left is from the Lake Observatory on the summit of Mount Hamilton in California, and the arrow points to where the AO setup is. On the right is a schematic of the Subaru telescope in Mauna Kea, and here is where the older AO system resides. This talk would be incomplete for me if I don't mention how I use AO for my research. My work is centered around an application of AO to directly image exoplanets and circumstellar disks. This is called high contrast imaging. The objective is to get images of faint objects at close angular separations from the host star, and hence requires high contrast as well as high resolution. It is achieved through the confluence of three techniques. One is AO, as we discussed earlier, and the other is extreme additive optics, which is a more advanced version. Here, the wavefront corrections happens at a much higher speed, and the DM can assume more complicated shapes due to having way more actuators. The second is coronography. We're using special devices, we can control the diffraction inside the telescope and mask out direct starlight, hence improving the contrast of our faint target. And finally, we need a way to disentangle the light from our target from that of the host star, which can usually manifest as speckles. For this, we need post-processing techniques. There's a lot more to discuss here, and that's another talk of its own. On the right is the illustration of high contrast imaging. It's a sequence of images on the HR8799 planetary system captured using the Keck telescope over a span of 10 years. The central part, which is marked by a little yellow star, is where the host star is supposed to be, but we've blocked it out through coronography. And you can see 4 little planets going around that center. AO has other applications as well. It's not just exclusive to astronomy. One application is in vision science, where we use it in surveillance cameras to provide real-time and long-distance imaging. It's also used by ophthalmologists to image the retina without aberrations to get a clear picture of the human eye. It is used in microscopes to correct aberration that comes from the samples, as well as to get images with deeper focus without having to move the objective of the microscope closer to the sample. Another application is free space optical communications, which is based on the transmission of light through an area of free space to transmit data. This uses horizontally propagating waves between optic components. This often leads to a high degree of turbulence and distortion of the light waves in the free space region. Additive optics can correct these disturbances and improve the transmission of data over long distances. The use of AO can also provide an increase in the speed of the telecommunication system. Finally, the biggest application area of AO is perhaps lasers. Some common applications that utilize lasers with AO include atomic trapping, understanding light matter interactions at the atomic level, laser cutting, quantum computing, and freeform metrology. Many of these laser applications are possible because AO enables the laser's beam shape and size to be controlled, which makes it more accurate, especially in the cutting and manufacturing of materials. I hope you were able to learn a lot about AO over here, and if you have any questions, you can reach me through Discord or Piazza. Thank you for your attention.
Register now on bit.ly/Intro2Astro 2024.